In this video, we'll do another example of curve sketching. So for the function f of x equals x squared minus 4 over x squared minus 2, we'll find the following properties, and then we'll sketch the graph. So I encourage you to pause at this point and try these steps out, try sketching the graph, and then you can see my solutions. All right, so what's the domain of this function? The domain of a rational function is all points at which the denominator is not equal to 0, if we're just looking at a polynomial over a polynomial. So the domain is where x squared minus 2 is not equal to 0. So let's see where it is equal to 0 to figure those points out. That would be at x squared equals 2. So x equals plus or minus the square root of 2 is where f of x does not exist. And so therefore our domain, this would be one way to describe it, x not equal to plus or minus the square root of 2 is a better way to describe it, and another way to describe it would be negative infinity up to negative square root of 2, as well as the interval from negative square root of 2 to positive square root of 2, as well as the interval from square root of 2 up to infinity. So that would be another way to describe the domain. Now let's find the first and second derivatives of the function. F prime of x, the first derivative is, using the quotient rule, low x squared minus 2 d high 2x minus high x squared minus 4 d low 2x again, all over the bottom squared, x squared minus 2 squared. So now that is the first derivative, but first of all, we're going to want to take the next derivative, and also we need to find the critical numbers. So we definitely want to simplify that. So let's go ahead and distribute on the numerator. So x squared times 2x, that gives us 2x cubed, minus 2 times 2x, that's minus 4x, minus, and x squared times 2x, that's 2x cubed, and then negative 4 times 2x, that's 8x, times negative, so plus 8x. And then on the bottom, we've still got x squared minus 2 squared. We don't need to multiply that out because it's actually good to have it in the factored form to see the zeros. So does this simplify at all? Yes. We've got a 2x cubed and a negative 2x cubed. We've got a negative 4x and a positive 4x that combine. So this simplifies to be 4x over x squared minus 2 squared. So that is our first derivative. Now let's look at what our second derivative is going to be, f double prime of x. Again, using the quotient rule, low x squared minus 2 squared, d high times 4 minus high 4x, d low. Here we need the chain rule. So 2 times x squared minus 2 to the 1 power, the outside function is something squared, multiplied by the derivative of the inside, that's 2x, all over the bottom squared. So that's x squared minus 2 squared squared again, that's x squared minus 2 to the 4th. Now, can we simplify this? One thing we might observe is that each term is a multiple of x squared minus 2, so we can cancel one x squared minus 2 from each term. Let's do that. And then we'd be left with, there's still one x squared minus 2 remaining times 4, minus 4x times 2 times 2x, so that's another 4x, times x squared minus 2 is canceled out, all divided by x squared minus 2, now just to the 3rd power. Continuing to simplify, we've got 4x squared minus 8 minus 16x squared, all over x squared minus 2 cubed. And one more simplification, we can combine the x squared terms, and so now we've got negative 12x squared minus 8 divided by x squared minus 2 cubed. So that is our second derivative in simplified form. Now for critical numbers, points where the first derivative either equals 0 or doesn't exist, points in the domain where that is true. So we saw that our first derivative, f prime of x, was 4x divided by x squared minus 2 squared. So now, where are the critical numbers for this? This f prime of x equals 0 when the numerator equals 0, when 4x equals 0. So that's going to be at the point x equals 0, so that is one critical number. F prime of x does not exist when the denominator equals 0, x squared minus 2 squared equals 0. But we already see that those are the 2 points that are not in the domain. So we see that x equal plus or minus square root of 2, as we saw above, are not in domain of the function. The function is not defined at those points. And so these are not critical numbers, but we are going to look at them when we think about intervals of increasing and decreasing. So let's look at that. The intervals over which the function is increasing and decreasing between critical numbers, x equals 0 is a critical number, as well as discontinuities of the function, places where the function does not exist, for example. So we see that our function is discontinuous at negative square root of 2 and positive square root of 2, the points that were not in the domain. So we're going to test the intervals in the first derivative in f prime of x to see if this function is if the derivative is positive or negative over these intervals, and determine whether the function, the original function, is increasing or decreasing over these intervals. So we're going to be looking at points in intervals between these critical numbers and discontinuities. Let's take a look at our first derivative. Our first derivative was 4x over x squared minus 2. Notice that the denominator is always greater than 0 because it's, or greater than or equal to 0 because it's a value that's squared. Whereas the numerator, 4x, is greater than 0 when x is greater than 0, less than 0 when x is less than 0. So we could go through and plug in specific points into the denominator, or into the derivative, but here it's a pretty clear-cut example that, as we said, the first derivative is negative for negative values of x and positive for positive values of x. And so this tells us that our function f of x is increasing over the intervals from 0 to square root of 2 and from square root of 2 to infinity. And f of x is decreasing over the intervals from negative infinity to negative square root of 2 and from negative square root of 2 up to 0. Note that at the critical numbers and discontinuities, the function is neither increasing or decreasing. At these particular discontinuities, the function is not defined at negative square root of 2 and positive square root of 2, so it can't be increasing or decreasing. And at f of x equals, at x equals 0, the derivative is 0, so it is neither increasing nor decreasing at that moment either. We can use this to see if there are any relative maxes or mins. So before 0, the function is always decreasing. So we're decreasing before 0 and increasing after 0. So that means x equals 0 is going to be a relative minimum. So x equals 0 is a relative min. And we can plug into the original function to see what that exact point is. So f of x was x squared minus 4 over x squared minus 2. F of 0 is 0 minus 4 over 0 minus 2. That's a positive 2. And so that means 0, 2 is a relative minimum for this function. So that will be useful for us later. Now we can find possible inflection points and concavity. Remember, that's based on the second derivative. Our second derivative was f double prime of x is equal to negative 12x squared minus 8 divided by x squared minus 2 cubed. So potential inflection points occur in the domain where the second derivative equals 0 or is not defined. Are there any places where the second derivative equals 0? Well, that would be if the numerator equals 0, negative 12x squared minus 8 equals 0. And does that ever occur? Well, this is negative 12x squared, a negative number minus 8. That is always going to be less than or equal to negative 8. So negative 12x squared minus 8 is never equal to 0. It's always less than or equal to negative 8. So the answer here is no. Are there any places where f double prime of x it does not exist? Yes, but these are not in the domain. So again, these would be places where the denominator equals 0, where x is plus or minus the square root of 2. And so those are not in the domain, but those are going to be important points for testing concavity. So this has no inflection points, no defined points where the function changes concavity. However, the function may still change concavity at the discontinuities at x equals negative square root of 2 and x equals positive square root of 2. So let's look at the second derivative and test those points. So we could test a point in between those values. We could test 0, we could test negative 2, and test positive 2 in the second derivative. So our second derivative, f double prime of x, is negative 12x squared minus 8 over x squared minus 2 cubed. As we observed, the numerator is always less than 0, so we just have to see what's going on in the denominator at these points. So f double prime of negative 2 is a negative value divided by negative 2 squared minus 2 all cubed. So that's 4 minus 2 cubed in the denominator, and so that's a negative over a positive, and that would be less than 0, so we're concave down there. F double prime of 0, that's a negative value over 0 minus 2 cubed, so that's a negative over a negative that's greater than 0, so we're concave up here. And f double prime of positive 2, we see we'll get the same as what we had for f double prime of negative 2. We'll have a negative value over a positive value, and so that's less than 0 as well, so negative. And this tells us that we're concave down over the intervals from negative infinity to negative square root of 2, as well as the interval from square root of 2 to positive infinity, and we're concave up on the interval from negative square root of 2 to positive square root of 2. And as we stated above, we have no inflection points, no points where the function is defined and the concavity changes. All right, so are there any horizontal asymptotes for this function? Remember, there's a horizontal asymptote if the limit as x goes to infinity of f of x is some number, some finite number, or the limit as x goes to negative infinity of f of x is some finite number. So if either of those things happen, then we've got a horizontal asymptote. Does that occur here? Well, yes. So if you look at the limit as x goes to infinity of x squared minus 4 divided by x squared minus 2, recall that if the highest powers in a rational function are the same, then this is just going to go to 1 over 1. This is just going to go to whatever the coefficients of the highest powers are, the ratio of those coefficients. So this limit is just 1. And similarly, the limit as x goes to negative infinity, in this case of f of x, will also be 1. So that tells us that we have a horizontal asymptote at y equals 1. So we have a horizontal asymptote at y equals 1. Do we have any vertical asymptotes? So those are places where the limit as x goes to c of f of x is positive or negative infinity, and it could also be as x approaches c from the left or the right. Does that occur for f of x is x squared minus 4 over x squared minus 2? Well, yes. So the places where the denominator equals 0 are going to give us vertical asymptote. So if we look at limit as x goes to, say, the square root of 2 of x squared minus 4 over x squared minus 2, we see that the denominator will be going to 0, while the numerator will go to square root of 2 squared minus 4, negative 2. So this could be going to 0 from the left or from the right, but in any case, this is going to be an infinite limit. It's going to be an infinite limit, and therefore we've got a vertical asymptote at x equals square root of 2, and we'll also have one at x equals negative square root of 2 for the same reason. All right, lastly, we want to look at the intercepts before we sketch the function. So the intercepts are where x equals 0, that's the y-intercept, or where y equals 0, that's the x-intercept, the place where it hits the x-axis. So we already know that f of 0 we've already computed to be 2. We saw that there was a relative min at that point back when we were looking at the first derivative. So we've got 0, 2 as the y-intercept. And where are the places where the output equals 0? So f of x equals 0 if the numerator equals 0. If x squared minus 4 equals 0, we see that that's going to happen when x is equal to plus or minus the square root of 4 at x equals plus or minus 2. So we do have two x-intercepts. We've got 0, negative 2, and 0, positive 2. So those are all of our intercepts. Now we just need to put together all of this information and sketch the function. So let's review what we've got. Let's review the information we've got so far and use it to sketch the function. So we know that f of x is decreasing from negative infinity to negative square root of 2. Negative square root of 2 is around there. So we know that it's decreasing up to that point. So up to this point it's decreasing. And it's also decreasing over the interval from negative square root of 2 to 0. So it's decreasing again over that interval, decreasing. And we know that the function is increasing over the intervals from, 0 to square root of 2, 0 up to square root of 2, increasing, and also increasing again over the interval from square root of 2 to infinity, increasing over those intervals. So we can plot that point as well, negative square root of 2. What else do we know? We know that it's concave up over the interval from negative square root of 2 to positive square root of 2. So we are concave up from negative square root of 2 up to positive square root of 2, concave up. And we know that we are concave down from negative square root of 2 to infinity, concave down, and from negative infinity to negative square root of 2, so concave down. Okay, what else do we know? We know we have no inflection points. We know that we do have a relative minimum at 0, 2. We know that this is going to be a relative min. We know we've got asymptotes, so let's plot those. We've got a horizontal asymptote, y equals 1. So we've got that horizontal asymptote, and we've got vertical asymptotes at plus and minus the square root of 2. So plus and minus square root of 2 are vertical asymptotes that match with the points at which the function changes concavity. Okay, we've also got some intercepts. 0, 2 was already included, but we've also got places where we hit the y-axis. We've got the point 0, negative 2 is an intercept, and 0, positive 2 is an intercept. All right, so let's see. In the middle, we know that this function is concave up. So the function is concave up over this interval from negative square root of 2 to positive square root of 2, and it's decreasing and then increasing. So decreasing and concave up, increasing and concave up. So that is what the function is doing in that middle portion. We know that before square root of negative 2, the function is decreasing and concave down, so it must be going along, hitting the vertical asymptote like so, and then going along hitting the horizontal asymptote like that. So that's decreasing, concave down, and then on the other side of positive square root of 2, we are increasing and concave down. So increasing, concave down, and going through that x-intercept. And that is the graph of our function f of x is x squared minus 4 over x squared minus 2.